Welcome back everyone. In this lecture actually I will prove Cartan's criterion for solvability and semi-simplicity. For that purpose we need to recall what we have done in the last class, which is actually primary decomposition theorem. So, let me actually state the Jordan-Chevalley decomposition, so which is a very important consequence of this primary decomposition theorem. So, I will state the result, so that way you can actually recall what we have done. So, as before we take V to be a finite dimensional space over complex numbers, and then we take T to be element of this endomorphism of V. So, then we actually prove the following. So, there exist unique elements S and N from this endomorphism of V satisfying the following conditions. The first condition, T can be written as S plus N. The second condition, S is semi-simple, N is nilpotent, the third condition, so both of them actually commute with each other and they also commute with T. So, we actually proved somewhat stronger. So, we proved that there exists polynomials P of x and Q of x such that this capital S and capital N, they are given by this polynomial in the T. Okay. So, there exist P of x, Q of x inside C x such that this capital S is given by P of t and capital N is given by Q of t. So, in that proof we actually indeed proved that this P of x and Q of x, they can be chosen so that the constant terms are being 0. Okay. In particularly we can assume P of 0 and Q of 0 both are 0. So, now it is very clear that both S and N commutes with T as well as they commute with each other. So, we proved that there exists unique S and N satisfying these three properties. So, that kind of decomposition we called it as Jordan-Chevalley decomposition, Jordan-Chevalley decomposition of this capital T. So, now once we have this decomposition, then it is clear that if we have these three spaces, let us say A is contained in B, B is contained in V, or subspaces such that T maps B to A. So, then we can immediately conclude S and N both actually map B to A. So, S of B again map to A and N of B is also mapped to A. Why? Because both S and N both are polynomial in T without any constant terms. So, because of that, if T maps B to A, then S and N both actually must map B to A. So, these are some consequence, immediate consequence of this Jordan-Chevalley decomposition. So, indeed we proved this existence of this Jordan-Chevalley decomposition using what is called primary decomposition. Okay. So, which I am not going to recall. So, for us what is important is this Jordan-Chevalley decomposition. So, now once we have the notion of Jordan-Chevalley decomposition, we can actually ask similar notions for any given operator and then its adjoint operator. Okay. So, here is a lemma. So, in case we have some x in endomorphism of V, and then assume that the dimension V is finite dimensional. So, we can also write let us say x equal to xs plus xn, which is the Jordan decomposition of this x. Okay, this is the Jordan-Chevalley decomposition of x. Then we can just apply the add map to these elements. So, then we have add x being equal to add xs plus add xn. Okay. So, now what we expect, naturally we expect this being the Jordan decomposition of add x. So, then this is the Jordan decomposition of add x. So, let us prove this. So, we can see that this x being xs plus xn. So, to prove that this add x equal to add xs plus add xn is actually the Jordan-Chevalley decomposition, we need to first verify add xn is being nilpotent and add xs is actually semi simple and so on. So, let us verify one by one. So, we already seen that if x is nilpotent, then add x is nilpotent. So, this is something we already seen. If x is nilpotent, so then that implies add x is nilpotent. So, the way we proved add x, you can write it as add x of y equal to x y minus y x. So, which is just difference between two maps, left multiplication and right multiplication. So, if we take this y, this is L x of y minus R x of y. So, since L x and R x commute and both L x and R x they are nilpotent. So, the difference of these two operators should be nilpotent. So, that implies that add x is nilpotent, that is how we prove. So, this implies add x is nilpotent. So, that means add xn is nilpotent. So, that is no worry. So, we need to check add xs y, that is semi simple. So, let us say we have a basis V 1 etcetera V n. So, this is the basis of capital V, and with respect to that x s looks like diagonal. So, this is the basis. So, this is diagonal. So, in particularly x s, so with respect to this basis V 1 etcetera V n, we have a basis for this endomorphism of V. That basis we denote it by E I j. So, this is the basis of let us say endomorphism of V. So, then with respect to that, this x s, the matrix can be written as some lambda 1 E 1 1 plus etcetera plus lambda n E n n, where this diagonal matrix looks like lambda 1 etcetera lambda n 0. So, now you can see that if I compute this add x s on this E I j, so then it is going to give us x s E I j minus E I j x s. So, which is equal to lambda I times E I j minus lambda j times E I j. So, that means this is lambda I minus lambda j times E I j. So, on the basis add x s acts as scalar. lambda I minus lambda j times E I j, and this is true for all I j. So, that means add access is actually diagnosable, and that implies access is add access is semi-simple. So, this proves that this add access is semi-simple and this add xn is nilpotent. So, we have this decomposition of add x into semi-simple plus nilpotent. To prove it is actually the Jordan-Chevalley decomposition, we need to check. So, these two operators actually commutes with x and as well as they are polynomial in add x. Okay. So, for that we can just see that add x xs will be just equal to add x bracket add xs. So, that means bracket x xs is 0. So, that will imply that add x bracket add xs is 0. Similarly, you can see that add x and add xn. So, they also commute because that is also same as add of x xn. So, this proves that add x commutes with add xs as well as add xn. Similarly, you can see that add xs and add xn, they also commute, as add xs bracket add xn is nothing but add of xs xn, which is 0. So, this means whatever that we wrote, these conditions are all satisfied. Add x is nothing but add xs plus add xn, and add x is semi simple and add xn is nilpotent. So, to prove uniqueness, we need to say that there are polynomials such that add xs can be written as polynomial in add x as well as add xn is written as polynomial in add x. So, it is enough to prove it for add xs because add xn is nothing but add x minus add xs. Okay. So, to prove the third part, claim is there exists p of x, or let us call it p z inside C z such that p of add x is nothing but add xs. Okay. So, this is again one can prove it using the similar ideas that we established before. So, to prove this, so we need to actually invoke that primary decomposition theorem. So, we can easily see that this how this add access is actually acting on this Eij, which is the basis. Okay. Again, this basis Eij, it is indeed obtained from by fixing the basis of this capital V. So, which has this diagonal entries lambda 1 etcetera lambda n. So, I will leave it to you to check because these arguments are going to again appear very often. Okay. So, it is actually a correct place for you to actually sit and check. So, if we take this lambda i's which are eigen values for x, okay, that is the relationship between the eigen values of xs and x. Okay. So, now we have this basis V 1 etcetera V n of this capital V. With respect to this basis, the operator xs written in terms of this diagonal operator lambda 1 etcetera lambda n. Now, using this we can see that this add xs how it acts on this Eij. So, again it is very explicitly given in terms of this lambda I minus lambda j acting on this Eij. So, now using this information you can locate a polynomial p of z such that this p of add x is exactly equal to add x's. I will leave it you to check this because this is very important point. Okay. So, now this proves that given this Chevalley decomposition of this x, we will be able to get Chevalley decomposition of this Jordan-Chevalley decomposition of this add x. Okay. So, now we will actually go back and then verify this one of the fact which is again like appears very similar to the one that we specified now. Okay. Again, so if you think about it, this is just locating this polynomial is nothing to do with only these eigenvalues. We can also choose some arbitrary complex numbers. Again, we can use this Chinese remainder theorem to actually locate this polynomial. So, let us try to do that, okay, which will be very useful again later. So, let me state that this as one lemma. So, what is this lemma says? So, if we have this operator, let us call it x again, acting on this finite dimensional vector space. So, now if we write this minimal polynomial of this x as some x minus lambda 1 power a 1 etc., maybe I will use different notation. So, let me call it z. Z minus lambda 1 power a 1 etc., z minus lambda r power a r. So, then we already proved that this V can be written as direct sum of these generalized eigenspaces. So, V can be written as V 1 direct sum etc., direct sum V r, where this V I is the generalized eigenspace which is given by the kernel of x minus lambda I identity power this A I. So, now what are we going to do? So, we just take some arbitrary complex numbers, call it mu 1 etc., mu r inside your complex numbers. So, now using this mu 1 etc., mu r, we can actually construct an operator that is acting on capital V. Okay, we can take some operator, call it T dash. So, that operator is just acting on V I by this scalar, let us say mu I. So, then that operator, okay, so which we actually, if you think about it, that operator will be of the form mu 1 identity on V 1 plus etc., plus mu r identity on V r. So, this is the operator that we are talking about. So, what one can prove? We can prove that even this operator which is written as diagonal operator or diagonalizable operator, for this operator also there is a polynomial p of z inside C z such that this p of x will be equal to this operator. So, this is something we did it for the lambda i's, okay, for the eigenvalues lambda i's. But now what we are saying, it does not matter whatever this diagonalizable operator that you take, for any operator you will be able to write this operator as polynomial in x. So, it is a very strong statement. Again, this also just follows from Chinese remainder theorem, nothing else. You can actually use the previous proof to prove the same thing. So, let us prove this because this is a very important statement that we made. So, what we do, we actually locate this polynomial, okay, using Chinese remainder theorem. choose this polynomial Pz such a way that this Pz is congruent to mu I modulo this z minus lambda I power a, okay, and this is true for each I 1 to r. So, since this z minus lambda I power a I, they are all actually pairwise relatively prime. So, we will be able to choose this P of z using Chinese remainder theorem such that this P of z is congruent to mu I modulo z minus lambda I power a. In particularly, this P of z can be written as mu I plus some q I of z as before times this z minus lambda I power a I. So, now by applying this evaluation operator, you can see that this is actually same as P x equal to mu I identity plus q I of x minus lambda I power a I, lambda I power a I. So, now if I take some vector capital small v in capital V I, you can see that if you evaluate P x of V I, then you get exactly mu I V I plus q I of x times x minus lambda I power a I V I, okay, some small V I in capital V. Note that this is going to be 0 as capital V I being the kernel of x minus lambda I power a I. So, that would imply P of x V I is equal to mu I V I. So, that means P of x restricted to capital V I is nothing but mu I times identity on this capital V I. So, this proves that this P of x is nothing but mu 1 identity V 1 plus etcetera plus mu r identity V r. Okay. So, this is somewhat very important. So, in particularly if you take basis of this capital V I and then take the disjoint union of those bases and then write down this matrix of this P of x with respect to that basis, then the matrix will look like this diagonal matrix mu 1 identity V 1 etcetera mu r identity V r. Okay. So, this is how the matrix will look like, diagonal matrix. So, this is something one can do it with any mu i's. So, in practice what we do, we actually take this complex conjugate of this lambda i's, okay, then we actually apply it for that. So, as an immediate corollary what we can see, so here is the immediate corollary. If I take x from this endomorphism of V and then if you assume this dimension V is finite and the minimal polynomial of this x is given by z minus lambda 1 power a 1 etcetera z power minus lambda r power a r, where this lambda 1 etcetera lambda r coming from C, they are distinct complex numbers. So, then you can see that you can take mu 1 to be lambda 1 bar etcetera mu r to be lambda r bar. So, then by previous argument there exists polynomial P z in C z such that this P of z is equal to lambda 1 bar identity on V 1 plus etcetera plus lambda r bar identity on V r. So, this is how we actually get, sorry, this is P of x. So, the operator lambda 1 bar 1 V 1 x plus etcetera lambda r bar 1 V r. So, that is going to be equal to this p of x. So, there exists a polynomial such that not only that diagonal operator lambda 1 etcetera lambda r, that is actually given in polynomial on x, even this lambda 1 bar identity v 1 plus etcetera lambda r bar identity v r, that is also given in polynomial of x. So, it is very strong statement. Now, this is going to be used in what follows. Okay. So, let me just use it. So, before that we can actually see that. So, if we write this x as, so this diagonal operator plus the nilpotent operator. So, this new operator that we have constructed, this lambda 1 bar etcetera lambda r bar. So, that is nothing but just x s bar. So, what is x s bar? So, x s bar is defined on this capital V. So, where x s bar on this V I is given by this lambda I bar identity V I. Okay. So, this is how one actually defines this x s bar. So, which is defined for this diagonalizable operator x s. So, now it is easy to check if we take this add x. So, which will be actually given by add x s plus add x n. So, we saw that if this is x equal to x s plus x n is Jordan-Chevalley decomposition. So, then this add x being equal to add x s plus add x n. So, that is also Jordan-Chevalley decomposition. So, in particularly we can talk about this add x s bar. So, if you think about it, this add x s bar is given in terms of this add x s bar. Okay. So, if you recall how this add x s acts on E I J. So, if we pick V 1 etcetera V n is the basis of capital V, with respect to that basis, if this x s is given by this diagonal matrix lambda 1 identity V 1 etcetera lambda r identity V r. So, then we saw that this add x s E I j is given by lambda I minus lambda j times E I j. So, this is the calculation that we did. So, in particularly if we take this add x s bar on E I j, so this will be given by lambda I minus lambda j bar E I j. So, this will be the definition. So, that means this add x s bar E I j is nothing but lambda I bar minus lambda j bar times E I j. So, if you think about it, this is exactly equal to this add x bar on this E I j, because add x s bar is also is diagonal operator, and if you do the calculation add x s bar on E I j is given by this lambda I bar minus lambda j bar acting on this E I j. So, that implies this add x s bar is same as add x bar. Okay. So, this is a small side observation. So, now we will use these observations in order to prove this Cartan criteria of for the solvability. So, before getting into this theorem, so first we will make some observation. So, we will see that where this actually result is coming from. So, if we start with G being solvable algebra, so then we know that using Lee's theorem, so we will be able to actually find a basis. So, you can assume G is being subalgebra of this GLV. So, let us assume this is the case. So, then by using this Lee's theorem, there exists a basis V 1 etcetera V n of this capital V, such that this G is sitting inside this what is called this upper triangular matrices T n comma C. Okay. This is all upper triangular matrices. So, this is what we have seen using the Lee's theorem. Now, if you think about it, because the derived algebra of this upper triangular matrices is nothing but strictly upper triangular matrices. So, this since T of n comma C comma T of n comma C, this sits inside what is called this strictly upper triangular matrices. Upper triangular matrices. So, we can see that the derived algebra GG is also sits inside this strictly upper triangular matrices. So, but it is not hard to see if we take capital A being upper triangular and capital B being strictly upper triangular. If we take the product capital A B, so then we can see that this must be strictly upper triangular. So, now using this observation, you can see that if we take trace of this x y, so trace of this x y where x is coming from G and then this y is coming from this derived algebra G G, which is we call it G dash, then you can see that the trace of x y must be 0. So, this is just direct consequence of Lee's theorem, because G there is a basis, with respect to that basis the elements of G made into upper triangular, in particularly the derived algebra elements made into strictly upper triangular. So, if we take the product of those two elements, then the trace must be 0, as the product being strictly upper triangular matrix. So, this is somewhat gives us some kind of trace condition to check whether given your Lie algebra is solvable or not. Indeed, we will prove that this is one of the characterization for solvability. Okay. So, we have already seen many characterizations for solvability from the definitions. For example, we proved that G is solvable if and only if add G is solvable. So, this is something we already proved. Okay. So, now we want to actually get some other criterion which is somewhat practically applicable. So, for that purpose we will see that this condition that we have written here, trace of x y being 0 for all x in G and y is in the derived algebra, is one of the characterization for solvability. So, this is called actually Cartan's first criterion. To prove this first criterion, first we will actually do it for what is called this linear subalgebras. Okay. Then we will actually apply for the general abstract Lie algebras. Okay, let us see how one can actually do this for linear Lie algebra. So, as before, we take V being finite dimensional vector space and G being subalgebra of this GL of V. So, suppose we have this trace of x y being 0 for all x y in G. Okay. So, then we can prove that G must be solvable. Note that here we have relaxed a bit the condition. We are demanding that the trace of x y is being 0 for all x y is in G. We will see later that this relaxation is good enough to say that G is being solvable. Okay. So, how do one prove this? So, in order to prove G being solvable, it is enough to prove the derived algebra is being nilpotent. Okay. So, to prove G dash the derived algebra is nilpotent. Okay. So, G dash, which is the bracket G G, is nilpotent implies G is solvable. So, this is something we already saw. This is again one of the characterization of G being solvable using Lee's theorem. Now, G dash is nilpotent comes from actually all the elements of G dash being nilpotent. So, that is from Engel's theorem. Okay. From Engel's theorem, so it is enough to prove that each element of this G dash is a nilpotent operator, nilpotent linear map. So, this is what we want to prove. So, in order to prove that, what we do, we use this Jordan-Chevalley decomposition. So, you take x being in G dash. So, then you write x equal to xs plus xn. So, this is your Jordan-Chevalley decomposition. So, in order to prove that x is actually nilpotent, so we need to prove that this xs, the semi-simple part, is actually 0. Okay. So, what we do, so we fix a basis since all these operators x, xs, xn, all of them mutually commute. So, and since xs being diagonalizable and xn being nilpotent, so we will be able to fix a basis of V. Okay, fix a basis of capital V. So, in which or with respect to that basis, so D is xs is diagonal, xs is diagonal and xn is nilpotent. So, nilpotent means it is actually strictly upper triangular, is strictly upper triangular. So, this we can do because all these operators actually commute with each other. Okay. So, since xs is diagonal, so we can call those diagonal entries to be lambda 1 etcetera lambda m. So, write this diagonal thing as lambda 1 etcetera lambda m, where m is the actually the dimension of the space. Okay. So, we fix the dimension of space to be m. So, now you can see that in order to prove this this xs being 0. So, to prove xs being 0, it is enough to prove these lambda is are being 0. So, in order to prove this lambda is are being 0, because we are working over complex numbers, what we will do, we actually take indirect approach, because we are going to use this trace criterion. So, we will actually try to prove that the summation lambda I bar, that is being 0 for summing over I ranging from 1 to n. Okay. So, this is where we are actually kind of going to use this trace criterion in order to prove lambda is are being 0. So, it is enough to prove the summation lambda I bar is 0. So, note that if we take this xs bar, which is the matrix whose diagonal entries, okay, again with respect to the same basis, you can take it to be lambda 1 bar etcetera lambda m bar. So, now what happens? So, if you compute this trace, the trace of this xs bar times your x, you can see that because x is nothing but xs plus xn, and xs bar times x will be xs bar times xs plus xs bar xn. So, this is being strictly upper triangular matrix, this is being diagonal matrix. You can see that the trace of xs bar times x is nothing but summation lambda I bar, where I range from 1 to m. Okay. So, in order to prove that the summation lambda I bar 0, so it is enough to prove the trace of xs bar times x is 0. But note that since this x is actually coming from this g dash, which is the bracket gg. So, in particularly x can be written as summation some bracket yi zi, where I range from some 1 to k. So, in order to prove this trace of xs bar times x is 0, so it is enough to prove the trace of xs bar times this yi zi, this is being 0. Okay. So, it is enough to prove this. Trace of xs bar times this bracket yi zi is being 0. But note that we already know this identity, the trace of A times BC is equal to trace of AB bracket AB times C. So, now if we use this identity, we can rewrite this trace into trace of xs bar yi bracket times zi. So, this is how we can rewrite. So, note that this yi and zi, they are all elements of this yi zi, they are all coming from your G. Okay. So, now to prove this trace of bracket xs bar yi times zi is being 0, you can actually see that this xs bar yi, so that is actually element of this G again. Okay. If this is true, so then we know that trace of this bracket xs bar yi zi is being 0. Why? Because this is element of G and this is element of G. For element of G, trace of xy being 0, that is what given to us. Okay. So, it is enough to prove that this xs bar, add xs bar maps this G to G. Okay. So, this is equivalent to saying add xs bar maps G to G. But why this is true? So, this is, you can see that add xs bar first of all is equal to add x s capital bar. Okay. So, we already seen from our earlier lemma. So, there exists a polynomial such that this add xs bar is actually given by polynomial in add x. So, now because this add x maps G to G, so that implies this polynomial in add x also maps G to G. So, that means this add x bar is also maps G to G. So, that proves that add x bar is actually maps G to G. So, that implies this bracket xs bar yi is being in G. So, that means this trace of this xs bar times yi bracket yi zi is 0. So, which says that the trace of xs times x is actually 0. So, that proves that summation lambda I bar is 0. So, that implies that lambda is 0. Okay. So, it is actually very tricky proof. So, but it really proves that this trace condition is indeed gives us solvability. Okay. So, now how to actually use this condition which is given for this linear Lie algebra to abstract Lie algebra. So, we will just use this adjoint map and then we know that L is solvable if and only if add L is solvable. So, using that we can actually get the first criterion for the solubility. So, here is the theorem. It is indeed corollary of what we have seen before. So, we take G being a complex Lie algebra. Okay, this is Lie algebra over complex numbers. So, then G is solvable if and only if trace of add x composition add y is 0 for all x in G and y in G dash. So, this is the trace condition for solvability. So, we already proved one way, if G is solvable then using Lie's theorem you can actually prove that like there exists a basis with respect to that basis, elements of this add x, x is in G, they all sit inside this upper triangular matrices. Okay. So, T and C. So, now using this information, this is just by Lee's theorem. So, as before, you can actually see that the trace of add x composition add y will be 0 for all x in G and y in G dash. So, this is just a consequence of this Lee's theorem. For the converse, if you assume this trace of add x composition add y is being 0 for all x in G and y in G dash, in particularly this is true for add x composition add y equal to 0 for all x y being in G dash. Okay. Now, G dash is nothing but what? G dash is nothing but the bracket G G. So, which is if you take the add of this, so then this is add of this G dash, which is add bracket G G, which is nothing but the bracket of add G add G. So, which is the bracket of add G dash, okay, add G dash. So, that means you can see that this trace condition add x composition add y being 0 for all x y in G dash immediately implies add G dash is solvable. So, since add G dash is solvable, so that will imply G dash is solvable. So, since G dash is solvable, that implies G is solvable. So, since solvability behaves very well with respect to the quotient, so we can see that under joint representation. So, add G dash is being solvable implies G is being solvable. So, that proves that G is solvable if and only if this it is enough to check this trace condition. Trace of add x composition add y is 0 for all x in G and y in G dash. So, this is a very important criterion to check solvability. So, we will see later that again like this trace condition is actually somewhat plays important role in order to actually check what is called semi simplicity and other things. I will stop here. I will continue next class with the criterion for the semi simplicity. Thank you.